And you'll see at the bottom left here, there's two sheets. There's an example on each sheet. So there's example 2 on sheet 2, back to sheet 1 has example 1. Okay, so we have a data set. We have a dependent variable y, and also known as the response, and two independent variables, x1 and x2. Now, the first thing I do is I always look at each of these individually, and I get the mean for each variable in the data set. So the mean of the y's, the mean of x1, and the mean of x2. I just always like to know, do an exploratory analysis this way. The medians are good to know too for each. And also the standard deviation. It's good to report those when you're working with data. It's good to know what each variable is on its own. It's also a good idea to plot the data before you run the regression to see if you have, and what you can do is plot y with x1, and you can also plot y with x2, so you have two separate plots, or you can plot it into a 3D scatter plot. Okay, so up here, if you go to File and you go to Options on the bottom here, Options, and you just click on add-ins. So I'm using an add-in package for Excel called the Analysis Tool Pack. And I think that is what you need, the Analysis Tool Pack. So if you just find that, you can search for it and then add it in and then just hit OK. Then, or you can even look for it that way if it doesn't just pop up. All right, so you can add that in. And what you can do then after that is just click the Data tab along the top. So you click Data and go over to the right to Data Analysis. So Data Analysis Tools, that's the add-in package. And just click it and you'll see you get a list of different analysis tools. We have the ANOVA. There's the ANOVA one factor there, the single factor that we looked at. You can get correlation, descriptive statistics. That's what these are down here. You know, the F test for two sample variances, histogram. You can make a histogram for each of the variables separately. And what we're interested in shows all the t-tests. What we're interested in is regression. So we want to run a regression, a multiple regression with these two variables. So I'm going to hit OK. So it says input the y range. So that's the dependent variable. So I will input that. So you just literally highlight the y range, that array, and then input x range. So I could put in just x1, or I could just use x2 and run a simple linear regression, or I can enter in the full range of both, just like that, and then just click this little arrow back down to close it. All right, and you can get some labels and all that. What we mostly want though is the output range, and I don't want it on a new worksheet. I want it right here so we can all see it. You can also do the residual plots and stuff, but we're just mostly interested in what the coefficients are. We want to know the coefficients, and we want to know then if those x1 and x2 are statistically significant and how good the model is and so forth. So here it is. So this is the output. It just does it automatically. So here's the summary output you get just by clicking that, entering in the data, and it does it all for you. All right, so multiple R we don't need to know in this course, but we do need to know R squared, which assesses the fit of the model. Remember, it's R squared is the coefficient of determination. And so we have a multiple regression here. So it's going to be a number obviously between 0 and 1, same as it is in simple regression, linear regression. And the closer it is to 1, the better the model. So we're looking at here 0.79, which is quite good. The adjusted R squared, we use it in multiple regression because as we add variables, independent variables to a model, that will automatically, just from the math, just from the formulas, that will automatically make R squared increase, which makes it artificially a good model. So the adjusted R squared will compensate for that. And you can see that from the formula. So we'll go back to the formulas. It's on the formula sheet that we were just looking at. You can compare the two. This value here is the standard error of the estimate. So that little, let me see if I have a pen, that little SE, you know, the little SE. So it's the standard error for the model, standard error of the estimate for the full model. Okay, and then we have the number of observations. The number of observations is 20, so we should have 20 rows here in our data set. So that means there were 20 rows. Okay. The output also gives an ANOVA table. So we're familiar with this really well. So the familiar, it gives you the regression, sums of squares, the degrees of freedom, the mean square for the regression, and it gives the same for the, now our Excel calls it residual, but we also call it error. You can also, I'll just type it in, error. Can also be called error. I'll just do that. I'll just put it in brackets. It's also the error. And then the total. So the total sums of squares and its corresponding degrees of freedom. And we know how to get them. The F is you take the mean square of the regression, divide it by the mean square for the error, and you get the F. And with Excel, they actually give you this significance F is the p-value. So I'll just put that above. That's the p-value, the exact p-value. So you don't need to look up the tables. But you might be given, say, in the quiz on Friday, you might be given a partial, like an incomplete ANOVA table or an incomplete table for the coefficients. And then you need to use your formula sheet to come up with the F value. And then you can use the F table for finding if there's significance. So you may be given some of this or all of it. Okay, degrees of freedom. For the regression, the degrees of freedom for the regression is 2, and that is equal to K. We call that K. So K is the number of independent variables. So we have X1 and X2, so that's why we have 2 there. For the error or the residual, it's going to be N subtract K subtract 1. So N subtract K subtract 1, where K is the number of independent variables, N we know is 20. We have 20 observations. So 20 subtract 3 gives us 17. Right, because N subtract K subtract 1 equals 17 in this case. And then for the total, it's N subtract 1. Well, we know there's 20 observations, subtract 1, and we get 19. So that's how the ANOVA table works. Then the sum of squares. So if we look at this sum of squares and we divide it by 2, so the sum of the squares for the regression divided by 2 should equal, as we know, should equal the mean square. So let's see if we can try that. Yeah, it's done the same, it's done very similar. The mean square for the regression is the same as the MSR for regression because it's tied in. So you can think of it as it's just using the same formulas. It's using similar formulas. Yeah. So let's look at this. If we take this value here, so I'm going to go equals. Whenever you're working with Excel and you're using it like a calculator, you always want to put an equals first in the cell. You can just pick any cell you want. And I'm going to click that one. And then I'm going to divide by this cell. And you guessed it, it should equal the mean square for the regression. And it does. 1577, 1577. So let's try another one. if I take, because I'm doing this because you might get an incomplete table. So you need to know how it all works. So let's say equals, if I take the mean or the sums of the squares for the error and divide by the sums of the degrees of freedom for the error, I'm going to get the mean square error. And I do 48.5. Likewise, we can get the F value. Let's check and see the F value. If I divide, so it's good to know where these formulas are coming from. That's why it's good to work in Excel to see how this works. So if I take the mean square for the regression, that cell, and divide by the mean square for the error, the mean square error, I should get the F value, the observed F. And that's what it is. 32.52. All right, and then from there, you can still, you could use this F value, and you could check and see if this is testing, remember, the ANOVA table for this is testing the overall model. And we have here, you can use the table or you can look up the significance. We have 1 point, it's very, 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 very small. So we have a very, very small p-value. What does a small p-value mean? It means we have a good model. It means that the overall fit of the model is good. The smaller the p-value is good, right? So you can go back to see what those null and alternative hypotheses are. But what we're always looking for is small p-values, because then we have statistical significance, which means according from the F test for the overall model, that's good. It means we have a good model. If the p-value had have been large, then we would be weary of this model or of using this model for any type of decision making or making conclusions. So the p-value is 1.54775 times 10 to the negative 6. Okay, so that's using scientific notation. That E negative 0.6 means take the number and multiply by 10 to the negative 6. So it's a very, 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 very small number, almost 0. So strong evidence to suggest we have a good model. That's consistent with our R-squared and our adjusted R-squared. Those are high. They're close to 1. They're high. They're decent. Okay. And the standard error, you know, that's the standard error of the model. That means 68% of the prediction should lie within 68%. Remember, plus or minus 1 standard deviation is 68% from the empirical rule. So would lie between, so it's going to be plus or minus 6.96 standard deviations. Now we look down here. Here's the coefficient. So what does this mean though? What's the model here? So for a multiple regression, here we go. For a multiple regression, we want y hat equals b naught plus b1 x1 plus b2 x2. We need subscripts on those x's. If we don't have subscripts on the x's, we won't be able to tell them apart. So if there's more than one independent variable x, then you need to use the subscripts to keep it straight. So which one's which? So this is our intercept. There's always an intercept. Most of the time we have an intercept. So it's 0.88. That would be our B naught. This is in the coefficients column. So 0.88 for B1, the coefficient for the predictor variable x. So this is for the variable 1. X variable 1 would be 14.59. So that would be B1, and B2, the coefficient B2 is 1.37, and that would be the coefficient for the X variable 2. Going to the next column, if everyone's with me, you can see we have the standard errors for these coefficients. So if we take this value, so if we take this coefficient, the intercept, and we divide by the standard error, Let's do that right in this cell. So if I equal this coefficient, divide by the standard error, I should get the test statistic, and I do. Okay, let's try another one. Let's see. If I take the coefficient for the x1, divide by its standard error. Remember, we don't have formal formulas for deriving these with multiple regression like we did with simple regression. So we need the software, and if you have those available, you can easily get this test statistic. So if you were given just the coefficients and standard errors, you just take the coefficient, divide by the standard error, and you get the test statistic. From the test statistic, you can use your t-table, right? The t-table that we've been using all along, and that is consistent. That works good. Let's try the last one. So if we take equals x2, so that would be the coefficient for x2, that would be b2, 1.37. Divide by its standard error, I get the test statistic for the x2 variable. And what each one has n minus k minus 1 degrees of freedom. So this is the degrees of freedom for each of these. That's for each of these variables. And if you look those up, so you look up the degrees of freedom, so it would be 17, right? 20 subtract 2. K is the number of independent variables, and subtract 1. That gives you 17 degrees of freedom. If you look these up for 17 degrees of freedom, you'll see that for the intercept, it's going to have a very high p-value. This one here is 0.04925. And so Excel gives us the exact p-value, where our t-table gives us a range, but we can still tell if there's statistical significance or not. Okay, so which one of these are statistically significant? From X, we don't usually care too much about the intercept, because the intercept is just where when both X's are 0. So we don't or when each X, yeah, it's just in multiple regression, the intercept is not really important, just like it's not really important in simple linear regression. What's important are these predictor variables, the independent variables, because how good are they going to be in predicting y hat? So you can look at the x1 and the x2 p-values and tell me whether you think if either of those are, so here's the question. Using alpha, we always use alpha at 0.05. I don't want to say always, but almost always. Which coefficients, x1 and x2 in example 1, are statistically significant? So hopefully the poll goes through this time. There we go. Only x1. If you want, I can go back to the Excel sheet. So is it just x1? Is it x2? Is it both? Let's go back to the Excel. Is it just x1 that's statistically significant? Is it x2? Both or neither? So what it's doing is it's testing the null hypothesis that the coefficient equals 0 versus the alternative hypothesis that it does not equal 0. That's what this is. This is how Excel is computing them for each variable on n minus k minus 1 degrees of freedom. So the answer is in front of you. You just have to remember how to do that interpretation. What does it mean? All right, good. Many of you are answering. We have a decent attendance. Just going to go back to the slides. All right, I'm going to end the poll, so lock in. All right. So I'm going to end the poll, share the results. The majority of you, 9 of you, said C, and that is correct. chose C, you got it. Because we're using alpha 0.05, which we usually do in these. I'm just going to highlight these. Those are the p-values that we want. Just going to grab some highlighting. There we go. So if you look at the first one, the p-value for the x1 variable is 0.049. So it's right on that. It's just below the threshold, right? So it is statistically significant. We can then conclude that we would reject the null hypothesis that coefficient does not equal. We would reject the null hypothesis of it equaling 0, means it does not equal 0, and therefore x1 is statistically significant in predicting y. Likewise, x variable 2, very, very small p-value, 0.001319. They're both, what is happening is we are testing the null hypothesis that these coefficients are equal to 0. So we're testing the null hypothesis that the coefficients equal 0 versus they do not equal 0. And when the p-value is small, we reject the null hypothesis. In both cases here, we would reject the null hypothesis because we just ran 2 t-tests. And when you reject, you automatically have statistical significance. And what that means in the case of these tests is both x1 and x2 are statistically significant variables, which means keep them both in the model, means that they both are valuable in predicting the y variable. Does that make sense? So we have statistics. This is when I run these regressions, and this is what I do a lot with my research. And the first thing my eye goes to, I look at the overall significance. I mostly really want to see this. I might have, 4 or 5 independent variables, but I want to, my eyes go straight to the p-values. I'm not really interested in these coefficients right away. I want to know, do I have statistical significance? Are those variables significant? And if they are, if I have a small p-value, then I have a good model. So this here, the F is being small. That means this, a small means this is a test for the overall model. That means that at least one of the means is different, right? So you have to think about, so that's actually a good thing. Yeah, so what you can do, I think the text, if I remember correctly, the text introduces the ANOVA with the simple linear regression and has the same, it will have the exact same interpretation. So if you want to review that on the F overall test, right? So whenever we have, remember what the F test is testing, it's testing for that the means are the same. So it's good in this case. It means it's a test for the overall model when you have, so that means we have, yeah, let me see. We can look at it closer. I just want to make sure that I don't deviate from the text too much, because we're just looking at regression in just a small segment. There are courses just on regression. That's how big the topic is. It's a very, very big topic. So I don't want to deviate too much. I do, though, want to go back to this adjusted R squared. If you take a look at the adjusted R squared formula, you can see even the formula for the R squared, we can, that wasn't a very good attempt at 3D, but some people can draw that a lot better. So we can see that the R squared is the SSR. I'm looking at this right here. The SSR divided by the SST, so the sum of the squares of the regression, divided by the sum of the squares of the total. So let's go and verify that. So let's take an equals. the sum of the squares of the regression divide by the sum of the squares of the total should give me r squared, and it does. The reason I'm doing this is you might be given just the ANOVA table, and a question might be, what is r squared? You should be able to just find that. So that works. And you can do the same thing with adjusted r squared. It's 1 subtract the sum of the squares of the error divided by its degrees of freedom, which is really, that's really just the mean square error in the numerator, divided by the sum of the squares of the total divided by n minus 1. So let's see if we can do that. So that's going to equal 1 subtract the mean square error for the errors, the mean square error, it's just that, divide by, I'm going to use brackets because I want to divide by that, divide by 19, close that bracket, close another bracket, voila, we have it, 0.76. So that's how you can get the adjusted r squared if you don't have, if you've only been given the ANOVA table. So you can think of, just going back to your question, to put it real simply, you can think of this ANOVA, it's a test for the overall model. And so you can think of it as small p-value, we have a good fit. Large p-value, the fit of the model is not really good. So we're going to be looking at goodness of fits. There's just 2 tests left in the very final module, module 12. So we're on the home stretch here, where we do similar things. We do similar with categorical data. Finally, over here, we have confidence intervals for each of these coefficients. So the intercept lower, so this is a 95% confidence interval. That's the lower, the minimum, the maximum. Same thing for the x variable, for the coefficient for the x variable is going to be between 0.05 and 0.29. So that's pretty wide. I don't worry too much about those. It's good to report. I could have given, I could have entered in the dialog box, I could have put in a 90% confidence interval. That's why these are just really redundant. It's just the same confidence intervals. They could almost be just deleted. They don't really add to it because they're just extra. So there you have it. That is multiple regression. Let's try another question. Just going to get it set up. See how we do here. What is the multiple regression for example 1? What is the final model? That's okay. Go ahead and ask lots of questions. I don't mind at all. It's good. It's good to ask questions. This is for you guys. This is what it's all about, for you to get not just the credit and the mark. It's also to be able to take this with you, to understand, to have the tools, because you never know when you'll need it. These are probably the most useful tools. It's ubiquitous running regression models in so what do we have there? Yeah, so the adjusted R squared is explained. Like I said, these are big topics. They are We have courses just on regression and multiple regression. So we're just sort of getting that overview. So I'll go back to the Excel sheet. What is going to be y hat? Well, let's see. Y hat equals, what are we going to put there? So some of you are in. So what are we going to choose? A, B, C, or D? Let's see. Is it that one? That one? Okay, I'm going to end the poll. I think many of you are in. All right. Okay, share the results. It's A. You're saying A. Right. So we would put for the B naught. B naught is going to be, come on. It just wants to go into a different mode here now. Anyways, B naught won't let me write. B naught is going to be, anyways, it's going to be 0.88. Won't let me write now. 0.88, 14 plus 14.59x times x1 plus 1.37 times x2. And that will be your, it doesn't want me to write. Anyways, it goes into a weird mode. I think I have to go into the drawing mode. Anyways, if you chose A, excellent. That's it. A is the correct answer. All right. Moving on to our second and last example. We look at, this is gender discrimination. It's well known that males make more money than females on average, and we can investigate it using a multiple regression. But we have a variable here, an interesting variable. So gender, well, gender is categorical, male and female. So what do? We can, and it's been entered in here. I need to get the draw so that you guys can see what I'm talking about here. Draw with touch. Okay, so I'm gonna put here males are 1, and you just simply give them what we call a dummy variable, or formally known as females is equal to 0. You assign them a number. So in this data set, the males are equal to 1. So the very first row, and I should also mention that the dependent variable is the salary, right? That's what we're interested in. It's in thousands, so it would be, I know it says 1.548, but it's in thousands, so it would be 1,548 for the first row. And the age is by 10 years, so this would be X1, and gender is X2. So the very first row, the data is a 32-year-old male that makes $1,548 per month. Okay. Second row is also a male, 38 years old, makes $1,629 per month. And I have done some summary statistics. The average monthly salary for the males is $1,578.625. And the average monthly salary for the females, though, is $1,091. And the average age is for the males is 32. The average age, though, for the females is younger, 35 versus 32. And we should also put how many we have of each. So how many males do we have? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. So 8 males, and we have 7 females. So we have a total of 15 employees from a particular industry. Now this is taken right from the textbook, so if you want to review it in more detail, it does come from the textbook, but we're going to run a regression here. I want to see, let's do exactly what we just did. Again, when you have categorical variables, you can enter them into the regression model by simply assigning a number. So let's say instead of males and females, let's say your data was temperatures and you had a high, medium, low temperature. It was in categories, then you could put a row for the lows and put a 1 and make the rest 0, whichever ones were low. And then the next column you would have for medium, you would put a 1 wherever the medium is, and then you could have another row for the high and put a 1 wherever it was high, and the rest are 0. So we call them dummy variables or indicator variables. When there's just 2, male and female, we can simply put them all in one row, right? 1 is males. It's just an arbitrary. I could have put, actually the text could have, it's their example. The females could have been 1, males 0. Okay, so you just have to keep it straight which one's which though for when you build the model. All right, let's grab the data tab, run the regression. I need to enter in. Okay, so we're going to enter in the the Y. We want to put in the Y, that's the dependent variable. Put in the X, so the age and the gender. So I'm highlighting both columns to get that full array. And then the output, let's put it right where that is so we can all see it. And I don't want anything else. I just want all that output. There we go. It just pops up. Okay, here's our regression statistics. R squared, looking good. 0.8 rounded to 2, 0.89. Adjusted R squared, 0.87. Standard error of the estimate for the model is 0.096. Observations, it's what we got, 15. Okay, we know how to find those. If you're just given the ANOVA table, you can extract those values from the ANOVA table or even a partial ANOVA table. We have, so just direct your attention straight to the significance. Do we have a good overall model? Yes, we do, right? Right there, small p-value, saying it's a decent model. That's consistent with the R and the R squared. We would also maybe want to look at the residual plots. The coefficients, there's the intercept. And X1, we know we entered X1 as age. And we know that X2 was gender. You have to keep everything straight on how you fed the data into the software. And then we have p-values. So you want to look straight over at the p-values. Do we have statistical significance? So I'm going to set out a poll, relaunch the poll. You tell me X1 and X2. So using alpha, again, of 0.05, is which variables are independent or it's statistically significant? X1, X2, both, or neither, based on that output. So here's the question here, using alpha of 0.05, which coefficients for X1, that's age, X2, gender, in example 2 are statistically significant? Only X1, only X2, both, or neither. So I'll come back to the Excel sheet so you can see. So it's A or 1. Yeah, A would be, A is going to be just X1. Put B if you think it's just X2. Put C if you think it's both. Both are statistically significant. And put D if you think neither are statistically significant. Remember the scientific notation, right? Remember that e to the negative 0.6. That means multiply the number before it times 10 to the negative 6. Okay, so that's a clue. 10, you're multiplying a number times 10 to the negative 6. All right. So back to the question, what do you think it is? I'll end the poll, share the results. Most of you have put D. So let's see, we have here. This is what we want to look at right there. I'm just going to highlight them. That's what we want to look at. So the first one, the p-value is 0.15 approximately, so it's out, right? We would say that it is not statistically significant. We have a high p-value. So that means that X1, age is not statistically significant. So I would probably not use age, right? It's not really going to help us in deciding whether we have discrimination. Also, but this value for the gender X2 variable, it is very small. That is 1.82311 multiplied by 10 to the negative 6. That is going to be very, very, very small. We have strong evidence. So it is statistically significant. And so that means that gender is statistically significant in predicting the monthly salary. So if you know if the employee is male or female, you can predict what their salary is going to be, which implies, right, gender discrimination. So the answer here, if you chose B, only gender, you got it right. Okay, so what, now here, when we look at it, this is coming from the Excel sheet. This is the multiple regression equation. And it is an intercept. So what we had y hat equals b naught plus b1 x1 plus b2 x2, right? b1 is age, or yeah, x1 is age, x2 is gender. So what we can do is we can fill in for the males. What would be the line if we sub in for the males? 0.732 plus, we'll keep the age just sort of, we would multiply by age, and 5.9 we would multiply by 1, right? Because we know that the indicator variable, the dummy variable, males, if it's males, it's equal to 1. That reduces down to an equation. If you work that all through, you end up getting actually it ends up being, if you can verify this, 1.191 plus 0.111 times age. So it reduces to a line, right? If you just look at the males, so our multiple regression equation ends up being just a line. It's not 3-dimensional, right? It's just going to have an intercept and a slope. The females, we can do the same thing, right? Remember the males were 1 and the females were 0. So the text, I think, shows this. So let's start with this. We're going to sub in for females. It's going to be, we're going to sub in 0. That is then going to reduce down. That's just going to go, right? That's just going to be 0. So it's just going to be 732 plus 0.111 age. It too has a line. And we can look at what this looks like visually. I'm just going to open up R because I prefer R for my plots. And here is the plot right here of the data showing on the Y, the monthly salary, on the X, the age in 10 years. The males are red circles, open circles, and the females are black open circles. And if I put those lines on, this is the what the multiple regression looks like. So they both have the same slope, but what is different is their intercept is different. So it's a shift. It's just a shift. Males up high. This really shows. And is the difference significant, statistically significant? Well, according to the output in Excel, the gender, right, the gender variable X2 was statistically significant. So this is showing that there is a difference in the salaries. Okay, I'm just going to go back so you can see the difference. So notice that they have the same slope. I'm just going to use a different color here. They have the same slope, but their intercepts are different. And the females clearly are much lower. So this is one way to do it. Now, if we switch the females with 1 and 0, would this change the numbers? Well, what would happen is it would change. It would change. You can even try that if you want. You can try changing it, but you would have to go back. If you do that, you can easily do that, but you would have to go back right to the source. So all these ones would change to 0. These would, you can even try it as an exercise, because I've given you the data. You have the Excel. What you would need to do is change these 1s to 0s, change these 0s to 1s, and then rerun it. But you'll still see the result will still be the same, as in terms of the females having lower monthly salaries. It will still be the same. And that's consistent with here, right? You can look, the average salary for the females is 1,091 and the males is 1,578. And the regression shows that gender is statistically significant. But yeah, if you did change it, but you can't just change it here, you have to go right back to the data, right to the raw data. So you can try it and see what the output is, but you should end up with the same result. All right. And something else though, now age, as you've seen, is not statistically significant. This, I'm actually surprised the textbook did this, because this is not really a good data set. What would you want instead of age? Like, would age really matter in this? I mean, it could, I guess, but what other variables what data would you want to get to really study this out fairly? Like, you wouldn't just look at gender. You wouldn't just go, okay, there's a difference between males and females. What other data, what other information would you want? What data would you want to collect on these people? Right. So what would we want for that? What kind of data do you think would be important? Anyone? You can just enter it in the chat. You're doing a study. You have a group of people. Country could, for ages we would need a higher range of ages. We would only have 20. Yeah, but what else though, other than age or country? What would really make one? What makes a person earn more money? Just think of it that way. So you have to think there could be, the males could have had something that experience, education. Those are two big ones that I was looking for. So suppose the males in this data set, there's 8 of them. What if they've been working at the company for 15 years? But the females, 7 females, what if they've only been there a year or 2? So that would be not fair to not have that data, because I think you would see a change if that was the case. That would really show a difference in our analysis. So to do a fair, proper regression study on gender discrimination, you would want to go, well, do the males have maybe more education or more experience than the females? So it has to be completely fair. Without those, you can't just go, well, gender and age, versus salary. It's not enough. And I've seen these studies where they have many, many different variables. There's a lot more involved to really determine and find the truth in that. Okay, so with that, let's take a look at this. So using the regression equation for example 2, what would be the predicted monthly salary for a 30-year-old female at this particular industry where they got the data from the where the textbook got the data? Yeah, it's interesting, isn't it? Okay, somebody else asked a question. Okay, do we need to do this on the Excel, like create the table and put the data on? It will help you. If you use the Excel, I have the Excel, I uploaded it. I have these 2 examples, and it will help you understand. Okay, so And you'll go, if you go through the questions in the textbook, they say use the software. So it will help you understand for the final exam and the quiz on Friday. No, you don't need to use it. It will be provided. The tables will be given to you on what you're analyzing. Then I just finished setting that quiz up, so that will be ready for tomorrow. Don't forget to hand in the assignment though too. Okay, it's better if you upload it to OWL. All right, so we have some answers coming in here. What are we going to do? We have a 30-year-old female. 30 and female. Now remember the original raw data. Age you want to enter in as 3.0. So it's going to be y hat equals 0.732 plus 0.111 multiplied by 3.0, and then the female part plus 0.459, and females were 0 in this case. Again, you could go back to the raw data and go, well, that doesn't seem fair. Let's give the females a 1. Then you need to restructure. You need to manipulate the data so that the males are 0 and the females are 1. You'll still get the same result though. It will still work out. All right. What have we got here? Slides number 8. I have an answer. So make sure you put 3.0. Don't just put in 30. Put 3.0 in. Double check it because some of you are giving a different answer. 3.0. 0.732 plus 0.111 times 3. That's it. No 0. Just times 3. Does that not change your answer? You're going with 4,000. I don't know. I'm going to end the poll because I'm not sure why you're picking, so many of you chose D. I got B, right? This is all going to 0. That's gone. So it's just 0.732 plus 0.111 times 3 equals 1.065, which is $1,065. Okay. We can't change our, you can't change your answers after, okay. I didn't realize I use Collaborate in OWL. It's like Zoom, but it's built into OWL. And students were able to change their answers. Okay, so here's our final question. 30-year-old male, what would be the prediction? 30-year-old male. That's not almost fair. We should be able to change our answers. So again, put 3.0 for the age. You can pick them all. Okay, I didn't know that. I haven't done enough polls on Zoom, I guess. I have set up a lot of polls. I actually haven't participated in the polls, in many polls. So, all right. So what do we have? Slide 9 should be okay. Now we're going in good. This is a good way to end the review. Good. Now gender is going to have a 1. So if you want to stay after, I can manipulate the data and change the genders, give the females 1 and the males 0, and see what the coefficients are, see if it all runs out. We can try it if you want. Okay, end the poll, share the results, and we get A, and the answer is yes, A. If you answered it, very good work. It means you're understanding multiple regression, and I think think that concludes everything. Yeah, good. So try out some of these examples. Don't forget to get the add-in, the data analysis. That way, when you click on data and go to data, you'll see this word data analysis. Okay, you need that to make it so you can have this summary output. All right, so everyone have a good day. I'm going to stop the clock and